Now let us look into another problem as per which there is a one-sided function f of t whose Laplace transform is given as f of s. From this we need to find Laplace transform of sin hat f of t, of course in terms of f of s. We know that sin hat is equal to e power at minus e power minus at divided by 2. From this, we can write that Laplace transform of sin hat f of t is equal to Laplace transform of half into e power at minus e power minus at multiplied by f of t. This can further be simplified as half multiplied by Laplace transform of e power at f of t minus Laplace transform of e power minus at f of t. We know that Laplace transform of e power at f of t is equal to f of s minus a. We also know that Laplace transform of e power minus at, Laplace transform of e power at f of t is f of s plus a, and Laplace transform of e power minus at f of a is f of s minus a. From this we can write that Laplace transform of sin hat f of t is equal to half into f of s plus a minus f of s minus a. So this is the required answer. Now let us look into another problem as per which there is an input of x of t which is a pulse from t is equal to 0 to 2 seconds, which is given as an input to a LTI system of impulse response h of t, which is a pulse from 0 to 1 second. We need to find if x of t is the input to the LTI system of impulse response h of t, we need to find the output y of t of the LTI system. From the given figures, we can write that x of t is equal to u of t minus u of t minus 2. From this, we can write that x of s is equal to Laplace transform of x of t is equal to 1 minus e power minus 2s divided by s. And if h of t is equal to u of t minus u of t minus 1, h of s can be written as 1 minus e power minus s divided by s. From this, the Laplace transform of the output y of t can be written as y of s is equal to x of s into h of s, which can further be simplified as 1 minus e power minus 2s multiplied by 1 minus e power minus s divided by s square. This is equal to 1 minus e power minus s minus e power minus 2s plus e power minus 3s divided by s square. From this, we can write that y of t is equal to L inverse of y of s is equal to t into u of t, which corresponds to the first term 1 by s square, minus t minus 1 into u of t minus 1, minus t minus 2 into u of t minus 2, which correspond to the second terms e power minus s by s square and e power minus 2s by s square, plus u of t minus 3 multiplied by u of t minus 3, which corresponds to the third term e power minus 3s by s square. So this is the Laplace transform, this is the convolution result of x of t and h of t. Upon plotting the same, we see that the output of the LTI system looks as a ramp from 0 to 1 second and a constant value from 1 to 2 second and a ramp with of declining slope from t equal to 2 to 3 second. So we got the output of the LTI system. Also, we plotted the same. Now, let us look into another problem. It's given that as per the problem, Laplace transform of for a one-sided function f of t, Laplace transform of t power n into f of t is equal to a into Laplace transform of t power n minus 1 into f of t. This is for a particular one-sided function f of t. We need to find that one-sided function f of t which satisfies this condition. We know that Laplace transform of t power n into f of t is equal to minus 1 whole power n divided by dn by dsn of f of s, where f of s is the Laplace transform of f of t. This is equal to a into, sorry, please note that a is greater than 0 as per the given data. So the right hand side term becomes minus 1 whole power n dn by dsn minus 1 of f of s. So we see that this is satisfied for every n greater than 0. So finally we see that upon solving the given differential equation, we see that f of s is equal to e power minus as. So it implies that f of t is equal to delta of t minus a. So the given equation is satisfied for the function f of t is equal to delta of t minus a, which is an impulse at the instant t is equal to a. So this is the required answer. Now let us look into another problem as per which there is an LTI system of impulse response h of t is equal to u of t minus u of t minus t. It's given an input of x of t which is equal to h of t, and it is given that y of t is the output of the LTI system, and we need to find integral minus infinity to plus infinity y of t. The Laplace transform of given h of t is given as h of s is equal to 1 minus e power minus st by s, which is equal to x of s. From this, we can say that y of s is equal to h of s multiplied by x of s, which is further equal to 1 minus e power minus st whole square divided by s square. This can simply be simplified as 1 minus 2 into e power minus st plus e power minus 2st divided by s square. So from this, the output y of t can be written as t into u of t, which is inverse Laplace transform of first term 1 by s square, minus 2 into t minus t u of t minus t, which is inverse Laplace transform of the second term e power minus st by s square plus t minus 2t multiplied by u of t minus 2t, which is inverse Laplace transform of the third term e power minus 2st divided by s square. From this, the output y of t can be plotted as shown. It's a triangular function in the range of 0 to t, with positive slope in the range of 0 to t and negative slope in the range of 0 to 2t, and having a peak magnitude of capital T. From this, we can say that integral minus infinity to plus infinity y of t is equal to area of y of t with time axis, which can be written as half into 2t into t, which is equal to t square. This is the required value, which is integral minus infinity to plus infinity y of t. Now let us look into another problem as per which we need to find the inverse Laplace transform of s square minus 3s plus 4 divided by s cube. We can simplify the given f of s as L inverse of 1 by s minus 3 by s square plus 4 by s cube, which can be written as u of t minus 3 into L inverse of 1 by s square, which is 3t u of t plus 4 into 1 by s cube, which can be written as 4 into t square by 2 u of t. Finally, upon simplification, this becomes 1 minus 3t plus 2t square u of t. So this is the required inverse Laplace transform. Now let us look into another problem, as a part of which we need to find the integral value integral 0 to infinity t into e power minus 2t sine of t dt. We know that Laplace transform of f of t can be written as integral 0 to infinity e power minus st f of t dt. So the Laplace transform of t into sine of t ut can be written as integral 0 to infinity e power minus st t sine t dt. So if we find out Laplace transform of t into sine t, this is equal to minus d by ds of 1 by s square plus 1. This is equal to 1 by s square plus 1, sorry, 2s by s square plus 1 whole square. From this we can say that integral 0 to infinity e power minus st t sine t dt is equal to 2s by s square plus 1 whole square. Upon substituting s is equal to 2 in the above integral, we get we get that integral 0 to infinity t into e power minus 2t sine t dt is equal to 2 into 2 divided by 2 square plus 1 whole square. This is equal to 4 by 25. From this, we can say that the required integral can be obtained using the Laplace transform, and the corresponding value is 4 by 25. Now, let us look into another problem in which we need to find the inverse Laplace transform of k into e power minus as divided by s square plus k square. We know that L inverse of k divided by s square plus k square is equal to sine of kt u of t. We also know that Laplace transform of f of t minus a, where a is greater than 0 and f of t is a one-sided function, can be written as e power minus as into f of s. From this, we can write that L inverse of k into e power minus as divided by s square plus k square is equal to sine of k into t minus a multiplied by u of t minus a. This is the required answer. Now, let us look into another problem, as per which there is a one-sided function f of t which satisfies the differential equation f double dash t plus f of t is equal to sine of bt. It's also given that f of 0 equal to f dash 0 is equal to 0. So we need to find the Laplace transform of f of t, that is f of s. So by taking the Laplace transform both sides for the given differential equations, we get that s square into f of s minus s into f of 0 minus f dash 0 plus s into f of s minus f of 0, because Laplace transform of f double dash t is s square into f of s minus s into f of 0 minus f dash 0. Similarly, Laplace transform of f of t is s into f of s minus f of 0. This is equal to Laplace transform of sine beta t, which can be written as beta divided by s square plus beta square. But it is given that f of 0 is 0 and f dash 0 is 0. From this, we can write that f of s is equal to, oh, sorry, please note that this is f of t, so Laplace transform of f of t is just f of s. So we can simplify that f of s is equal to beta divided by s square plus beta square multiplied by s 1 plus s square. So from this we see that the Laplace transform of the one-sided function given is f of s is equal to beta by s square plus beta square multiplied by 1 plus s square. Now let us look into another problem as per which there is an LTI system of impulse response, sorry, of transfer function g of s is equal to 2 by s into s plus 1 into s plus 2. We need to find the impulse response of the LTI system. The given transfer function g of s can be split into partial fractions as shown. So g of s is equal to 2 by s into s plus 1 multiplied by s plus 2. So g of s upon splitting into partial fractions becomes as shown. So it will be g of s will be equal to 1 by s and 1 by s plus 1, sorry, minus 2 by s plus 1 plus 2 by, sorry, 1 by s plus 2. So from this we can write that the impulse response of the LTI system is g of t is equal to L inverse of g of s is equal to 1 minus 2 into e power minus t plus e power minus 2t u of t. So this is the impulse response of the LTI system. Now let us look into another problem using which we need to find Laplace transform of t into cos of a t u of t. We know that Laplace transform of cos of a t u of t is equal to s by s square plus a square. So we also know that Laplace transform of t power n into f of t is minus 1 whole power n dn s divided by dsn f of s, that is nth derivative of f of s. From this we can write that Laplace transform of t into cos a t u of t is equal to minus d by ds of s divided by s square plus a square, which upon simplification becomes minus of s square minus a square, sorry, plus s square minus a square divided by s square plus a square whole square. This is upon finding the nth derivative of, sorry, it upon finding the derivative of s by s square plus a square. So from this we see that the Laplace transform of t into cos a t u of t is equal to s in s square minus a square divided by s square plus a square whole square. Now let us start looking into another problem as per which we need to find Laplace transform of 1 by t multiplied by 1 minus e power minus t u of t. We know that Laplace transform of 1 minus e power minus t u of t is equal to 1 by s minus 1 by s plus 1, because Laplace transform of u of t is 1 by s and Laplace transform of e power minus t u of t is 1 by s plus 1. From this we can write that Laplace transform of 1 by t multiplied by 1 minus e power minus t u of t is equal to integral s to infinity 1 by s minus 1 by s plus 1 ds. This is because of the reason that Laplace transform of 1 by t into f of t is equal to integral s to infinity f of s ds. So this can further be simplified as log of s by s plus 1 with limits being from infinity to s. So the same further gets simplified to limit s tends to infinity log of s divided by s plus 1 minus log of s divided by s plus 1. We know that as s tends to infinity, this term becomes 0. From this, the Laplace transform value becomes minus log of s by s plus 1. This can further be simplified as log of s plus 1 divided by s. This is because of the reason that minus log a is equal to log of 1 by a. Using this identity, we see that the required Laplace transform is log of s plus 1 divided by s. Now let us look into another problem as per which we need to find Laplace transform of cos of at minus cos of bt divided by t u of t. We know that Laplace transform of cos of at minus cos of bt u of t is equal to s by s square plus a square minus s by s square plus b square. From this we see that Laplace transform of 1 by t multiplied by cos at minus cos bt u of t is equal to integral s to infinity s by s square plus a square minus s by s square plus b square ds. This is equal to half log of a square plus a square minus log of a square plus b square, with limits being from infinity to s. Finally, upon simplifying this, we get that the required Laplace transform value is log of square root of a square plus b square divided by a square plus a square. So from this we see that the required Laplace transform, that is Laplace transform of cos at minus cos bt by t u of t, is equal to log of square root of a square plus b square divided by a square plus a square.